Alright, this is the fifth example of composition of function. So we are given a function f of x equal to 2 over x plus 4 and g of x equal x squared minus 2. Let's find the domain of each of these functions first. Well, for the function g, it's pretty obvious. Since we don't have any denominator, that means we don't have any point of discontinuity, so the domain is going to be all real numbers. Now for the function f, it is a rational function, so the first thing I like to do is try to see if I can factor it out. Well, we cannot factor out this rational function, so we can take the denominator x plus 4 and set it not equal to 0, and this is the setup for finding the domain of any rational function. Solving for x, we get x cannot be equal to -4, so that means the domain is going to be all real numbers except x cannot be equal to -4. And if you were to write it in interval notation, we'll sketch a number line first, like this. And let's say -4 is here, and 0 is here, and I'm just going to put a 0 there because, it makes it easier for me to see. We are excluding x equal to -4, so put an open circle right there. By reading the number line from left to right, we are going from -infinity up to -4, but not including -4. So this part here has the open interval from -infinity to -4, and then put the parentheses right there. Now for the part from here all the way to here, we are going from excluding 4 all the way to positive infinity. So put the union, which is a word or, and then parentheses at -4 and all the way to positive infinity. So this is the interval notation for the domain of the function f. Now let's find f of g of x. Well, f of g of x is basically take the entire function g and replace all of the x of the f function, which is just this one right here. So f of g of x, take the whole g function, replace all of the x of the f, which is the outside function, with that g function. So that means we are going to have 2 divided by x squared minus 2 and then plus 4, like that. What is this going to give us? Well, let's simplify a little more. Well, we have the invisible positive 1 on the front, so 1 multiply anything just by itself. So we got 2 over x squared minus 2 plus 4. Combining like terms, we got x squared plus 2 under 2, yeah. And for the real numbers, if I take a look at this denominator, well, this denominator is always not going to be equal to 0 no matter what, because it is always going to be positive. So the domain of this result is going to be all real numbers. What about the step where we plugged in the function g? For the inner function g, its domain is also all real numbers. It doesn't have any restriction, just like how it doesn't have any restriction for this result here. So the domain of this compositional function is actually all real numbers as well. Okay, now so that's just for real numbers. How about imaginary numbers? And the reason why I want to throw it in is because for imaginary / complex number, well, it's because I recognize the fact that if I take this denominator, x squared plus 2 not equal to 0, and I solve for x, I want to have x equal plus or minus square root of -2, which is equal to plus or minus I times positive square root of 2, because remember that -2 in here can be rewritten as -1 times 2. Or should I say the square root of -2? So square root of negative 2 can be rewritten as the square root of negative 1 times 2, and then separate it out using the loss of exponent. This becomes I, and this stays. So that's why you get that. So that's for complex numbers, okay? So that's a fun fact. Now what about g of f of x? Well, for g of f of x, well, let's see. The function g, the function f is right here, and it is this whole thing. So we are going to take the entire f function and replace all of the x of the g function, which is just this one, and we keep the exponential power. So this one we are going to have 2 over x plus 4 raised to the second power, and then minus 2. Well, this is going to give us, let's say, 2 over x plus 4 raised to the second power is going to be 4 over x plus 4 raised to the second power, and then minus 2. So for this one, I can just take for this result here, I can just take the denominator and set it not equal to 0. Now the denominator is x plus 4 raised to the second, so I gotta include this exponential power as well. Take the square root of both sides. I get x plus 4 not equal to 0, so x cannot be equal to negative 4. So this resultant function has a restriction of x equal to negative 4. Now, what about the restriction of the inside function f? Well, if we take a look at the domain of the inside function f, it also has a restriction of x equal to negative 4. So that means taking in all of the restrictions of both the result, which is x equal to negative 4, and the inside function f, which is also x not equal to negative 4, the domain of this whole thing is going to be all real numbers except except x cannot be equal to negative 4. And on the number line, how do you write the interval notation? On the number line, you got negative 4 here, and we are excluding negative 4. So put the open circle right there. So going from left to right on the number line, we want to go from negative infinity up to negative 4, but not including it. So that means this part that I just shaded has the open interval notation of negative infinity, comma, negative 4. Now what about this part on the right side of the negative 4? So that's when we put the union, which stands for the word or. And then we are going to have open parentheses again, because we are still excluding negative 4. And then we go all the way to positive infinity, like that. So this is the interval notation for the domain of this composition of function, g of f of x. So yeah, the idea is that, as usual, when you do composition of function, you take one function, you put it inside another, and then you find the domain of each, you find the domain of each function first. And then you take one function, put it inside another, and then you do the algebra, you get your result. Take your result, find the domain of the result, and then go back to your inner function, look at the domain of your inner function to see whether or not there's any restriction, and if there is, how many of the restrictions. After that, you're going to include all of the restrictions of the inner function and your result to come up with the domain of the entire composition of function.